Now in this presentation we are going to find out the logical expression for your sum and the logical expression for your output carry, so that if you want to make an adder circuit you can make it. This box you can see here is your full adder, and what is inside this box, actually the combination of your logic gates we don't know. And you can see that A, B and C input are the three inputs to this full adder, and the sum and your carry output are the two outputs of your full adder. Okay, so how we are going to find out the logical expression, or you can say that the combination of the gate inside this box? We will do it by using the Karnaugh map. So I have already made the table for your inputs, that is A, B and Ci, and depending upon this input and by using the concept of addition we will try to find out the sum and the output carry. Very easy. I hope you have followed my presentations so that you know how to add the binary numbers. We are going to add A, B and Ci to get the sum and the carry output. So in your first case both A, B is 0 and also the carry input is 0. So the sum is definitely going to be 0, and also there is no carry output, so it is also 0. Now A plus B, 0 plus 0 is 0 and 0 plus 1 is going to be 1, so sum is 1 and there is no carry generated, so the carry output is 0. So in our third case A is 0, B is 1, so A plus B, 0 plus 1 is your 1, and 1 plus 0 gives you 1. So again sum is 1 but the carry output is 0. In our fourth case A is 0, B is 1, so 0 plus 1 is 1, and 1 plus 1, the carry input is 1, so 1 plus 1, sum is 0 and there is 1 carry. Now most of you might be thinking that how this thing is possible, 1 plus 1 is 0 and with 1 carry. So let's see it here. Actually this is an extra work that I am doing right now, because in my one of the lectures I have completed this thing in a great detail, so it is recommended to you to go to that lecture from the playlist. But if you don't want to do that, then let's see it here. Let's take a decimal number 7 and add it with another decimal number 6. So you are very good in these things, the decimal addition. 7 plus 6 gives you what? 13. So you write 3 here, and it gives carry 1, and of course here it is 0, and also 0 7 is there, so carry is 1. So 1 plus 0 gives you 1, so you say that the result is 13. So did you ever thought that why we took this 1 as a carry and just placed it here? It is because that in decimal the base is represented by R, the radix is same thing, and R is your 10. Okay, so in decimal the base is 10, and whenever you complete a base in the addition you just put forward the 1 and keep the remaining thing. For example, in 7 plus 6 we are having 13, we know it is 13, and 13 can be written as 10 plus 3. So 10 is the base, so we just added 1 at the next weight. Actually it is all dependent on the weight, they are all weighted codes, so we put 1 here and the 3 we keep, and that is why we do this thing in the binary. Because when you add 1 then what actually happens? 1 is what? 2, and in binary the base is 2, so 2 can be written as 2 plus 0. So we will put a carry here and we will make the result 0, we will keep the result 0, like we kept 3 here. So you just remember that we want to make the base, and the rest number we will keep, and whatever the base we will put forward it as the carry. So we will keep 0 and 1 as the carry, so the carry output is 1 and the sum is equal to what? 0. So that's why we did it here. Actually it's all dependent upon the weighted codes, so it will be much better if I explain you by taking the weight of the corresponding positions, but it will be really out of scope of this presentation, because I have to complete this presentation in the limited time, the full adder circuit part, and I cannot explain you this addition of the binary numbers. For that, go to the playlist and in that search the binary addition. You will find it very easy to understand. So let's move to our circuit part. Now in our this case, the fifth case, A is 1, B is 0, so 1 plus 0 is 1, and Ci is 0, so 1 plus 0 is again 1. Sum is 1 and carry output is going to be 0. In this case, 1 plus 0 gives you 1. Let's do it. 1 plus 0 gives you 1, and 1 plus 1 gives you 0. So the sum is 0 but the carry is 1, like this case. In this, 1 plus 1 gives you 0 and carries 1, and 0 plus 0 gives you 0 with carry 1. Again in the last case, 1 plus 1 gives you 0 with carry 1, and 0 plus 1 gives you 1. So there is sum 1 and carry also equal to 1. Now we got our sum and also the carry output. So the next step is to make 8 variable K map. Why 8 variable K map? Because there are 3 variables involved, and 2 to the power 3 gives you 8. So there are total 8 cells K map. So this is our 8 cell K map. We will write first the MSB, which is A, then B, and then LSB CI. This is your 0 0 0 1 1 1 1 0 0 1, and let me copy this K map because we are going to need this K map or the K map like this exactly when we are solving the carry output. So let's copy it down, and now we'll move to fill up this map. So let's fill it down. It is for sum, and this K map is for the carry output. So 0 1 1 0, so 0 1 1 0 1 0 0 1, so 1 0 0 1. Now you can see here that a very interesting pattern is appeared. Why it is interesting? Because you will find that you cannot group any of the ones together. This one cannot be grouped with any of the ones. Similarly, this one, and this one. And this particular pattern we call as checkboard configuration. Checkboard configuration, and it is something I have explained you when we were in the lecture of your parity checkers. Okay, so this is the checkboard configuration, and if you studied that lecture, then you might be knowing the result without solving this thing. So let me write it down directly. The sum is equal to A XOR B XOR Ci. So you have to remember one thing in the checkboard configuration is that whenever it appears, the output, the sum, is equal to the XOR combination of the all inputs. For example, if we were having the 4 inputs A, B, C, D, then the sum should be what? A XOR, so S should be what? It is not the sum. S is any function. S is equal to A XOR B XOR C XOR D. So you have to just take the XOR operation of the given inputs in case of checkboard configuration. Now we are going to find out what is the value of C0 or C output by using this K map. So let's fill it down. 0 0 0 1, so 0 0 0 1, 0 1 1 and 1, so 0 1 1 and 1. So we don't have any checkboard configuration in this case, so let's make the groups. The first group that I will make is the group of these two ones, then this is our second group, and this one is our last group. This is the simplest thing that anyone will do with this particular K map, but there is a twist that we will see after this, after finding the values of this particular implicants. So C output is what? From the first group we are going to get BCI, or from the second group we are going to get A, and Ci is changing from 1 to 0, so it will be 1, and B is same and it is 1, so A B. Similarly, from the third group we are having A and Ci. So this is what we are going to get if I just directly solve this K map. But there is one way also this C out is written in many books, is that A, B or Ci A XOR B. You will find this thing very common in many books. So if I ask you to find this function by using this K map, it will be very difficult for you. You will just try time and time and you are not going to get this function. Why? Because you will try to follow the procedure that we used to do in the K map. That is, we will try to combine the greatest possible group of ones. But if you want to get this function, you have to just leave that particular procedure of the K map and do what I am doing right now. Just fill it. So it is your 0. Let's do this with different color. This is 0 0 1 0 0 1 1 1. Now I will make the group of these two ones, okay, and I will keep this one alone and this one too. So what I did, I didn't combine this two one with any of the other ones. I kept them alone. And let's see what we are getting by doing that. I'm having AB from this group, definitely, like we got in this case, and A B complement Ci from this one. This is A B complement and Ci. Similarly, from this one I'm going to get A complement B Ci. So A complement B Ci. The next thing I can do is to take something common from these two terms. So I think I'm getting Ci as common, so Ci is common, and inside the bracket I'm having A bar B, and I think we are having our result, that is A XOR B, the same thing that I have written here. So this is how the carry output is represented by using these two ways in the K map. So at the end of this presentation we are having our sum as A XOR B XOR Ci and having our carry output, and it is very easy for you to implement this as a circuit. I'm not going to do that part. You can definitely take a 2 input XOR gate, and if you are taking the 2 input XOR gate, you are going to have the two such type of gates, or you can use directly a 3 input XOR gate. Your A will be here, your B will be here. This is your A XOR B, and in this gate one of the input is your C input, so that sum is here and you are having it is A XOR B XOR Ci. Similarly, you can implement the carry output. This is something you can do it by yourself. So in the next presentation we will